So, welcome to this course Field Programmable Gate Arrays Based Signal Processing Systems. The lecture 1 is Introduction to FPGA, offering this course by Professor P. Sumathi, Department of Electrical Engineering, IIT Roorkee. So, the first introduction starts with the FPGAs. The FPGAs are Field Programmable Gate Arrays. The full form is Field Programmable Gate Arrays. It's a chip. We all know that this FPGA is an embedded chip. It's like any other chip, integrated circuits IC. It's a digital processing component. We use this for deploying the digital circuits. So, it is called this embedded chip. It provides the hardware architecture. It contains, or it has this hardware architecture. The hardware can be programmed to describe a specific hardware component. The specific hardware component in the sense that FPGA is, that component can be programmable and reconfigurable also. So, the hardware device could be programmable and reconfigurable. This is especially used for digital systems deployment or implementation of these digital systems. That is the main advantage of this field programmable gate arrays. When we say this FPGA, it's a hardware matrix, like it contains the logic gates, and this logic gates can be used for implementing different functions of digital in nature, and these different functions can be interconnected by selecting different routes. That routes are actually placed on this architecture itself. So, we can call this FPGA as a 2D structure or the matrix, hardware matrix, and these routes especially which connects the different logic blocks are wires or routes which are programmable. That means it can be defined to do certain task, like it can be considered as a single bit line or a wire, and these device attributes are especially cost, capacity, speed and power. So, how we maximize these things, like if you consider the cost, how do we check the cost would be a minimum for this device in the design. Also, the capacity should be maximized and speed should be good and the power should be minimized. So, these are the device attributes especially applicable to the field programmable gate arrays. So, here is the architecture, FPGA generic architecture, which is seen in the figure. The first, it contains the logic block. We can see here over here the logic block, and they like to choose some. So, the second logic blocks 2, 3 and 4, it is especially a 4x4 architecture, generic FPGA architecture. So, you can see the first row of logic blocks and the second row of logic blocks 1, 2, 3, 4, and the third row of logic blocks, also the fourth row of logic blocks. In each row there are 4 and in column there are 4. So, it's a 4x4 matrix like structure of this architecture. And then we could also very well see that there are lines connecting in the row wise and the column wise. So, the row wise lines are called the row interconnects, and the column wise ones which are connecting the circles, we will come to that. What is that circles meaning? That is called the column interconnects. So, there are row interconnects and column interconnects. So, apart from row interconnects and column interconnects, we have the switches as shown as the circles. The switches also are part of the architecture, and after this we have an IOs which are placed over all the sides of the architecture, that is FPGAs. So, these are IOs, input output pins, or IO blocks, we call them as IO blocks. So, in that, if you see this is an array of programmable logic blocks, and these have the interconnects, also the field programmable switches. So, the logic blocks are programmable, especially if you consider this programmable array of logic blocks. It consists of LUTs and the flip-flops, also multiplexes So, in combination, the number of LUTs, flip-flops and multiplexers will vary, depends on the architecture. Okay. So, the vendors try to introduce more and more LUTs, flip-flops and multiplexers in the logic blocks. These are also called CLABs, that is configurable array logic array blocks also. So, the CLABs contains LUTs, flip-flops and multiplexers, and these are also called slices. In some of the architecture, these are called slices. So, the slice would contain LUTs and flip-flops and multiplexers. So, the LUTs will take n inputs, the LUTs would contain, will take L inputs and give the output accordingly, whatever the function to be implemented on the LUTs. So, if this can be a 3 input LUT or 2 input LUT, it depends on, initially it was 2 input LUTs and then 3 input LUTs, and then it varied, it keeps increasing as the architecture grown in many ways. So, this is the LUT part, and we have this flip-flops as well. So, that flip-flops can be utilized to are programmed to have the digital circuits. So, what is to be implemented, the functionality of the digital circuits are implemented in this flip-flops, and multiplexers also can be chosen accordingly, depends on the design of the digital circuits. So, whatever the digital circuits we have, the functionality, either suppose it can be a simple NAND gate or AND gate or XOR gate. These gates can be implemented to start with. These are the very simple digital circuits, and then we move on. This can be even combinational circuits can be deployed in it, or programmed using the logic blocks. Also, the sequential circuits, digital circuits can be deployed in this. So, these logic blocks is utilized in the design, especially FPGA design, that is the digital circuits in the design, digital combinational or the sequential circuits that can be using these logic blocks. These are configurable and these are programmable as well. And if we look at the next part of this, interconnects, these interconnects where the row interconnect and the column interconnects. So, row interconnects and column interconnects both are programmable in the sense, we can consider this as a single bit. It is selectable. Actually, we can select which interconnect can be used to connect the logic blocks which are closer by. So, every logic block will contain LUTs, flip-flop and multiplexers, but the interconnects will choose the EDA tool. Actually, it is a choice of EDA tool, but choose the smaller short interconnects to avoid the delays and the improvement in the performance. So, here the interconnects are also programmable. These are the row interconnects and column interconnects which are used for the communication of these logic blocks. It connects between the logic blocks. So, the logic blocks are connected by the interconnects, and it uses the next part as switches, that is the switches are the field programmable switches. So, these switches are either made of pass transistors or a tri-state buffer. So, pass transistor or tri-state buffers can be utilized in this switches. So, we have the switch, when you say this field programmable switch, it is a block actually, again it is a switch block which contains multiple switches. So, suppose here it is in the figure, it is shown there are 3 lines. So, each contains switches, 3 switches in the switch block. So, instead of saying it as a switch, the switch block contains the switches which chooses the lines, the row interconnects or the column interconnects according to the design, the digital design which we are going to do in this course. So, this is about the generic array of FPGA architecture which has 2 by 2 structure, like for example, we have shown 4 by 4 structure. So, when you come to the programmability of the design FPGA, so we have this 4 by 4, I have shown in the previous slide that it is a 4 by 4 generic architecture, FPGA architecture, in that it is a physical hardware in which we are selecting the logic blocks and we are selecting the flip flops, multiplexer and the LUTs to implement a Boolean function digital circuits. So, it is a selection of the programming is nothing but selection of these physical hardware of the FPGAs. So, it is programming the physical hardware, and but it is different, especially different from the general purpose other processors. So, other processors or embedded processors, GPUs and DSPs are in all of this the programming concept is different, wherein you write a code, you write a code and then run that on a predefined hardware. So, here the programming meaning in the FPGA is different from the programming in other softwares. So, a dedicated software is programmed and executed with the hardware already available one that is being exploited in the programming process, that is it is executing fixed functionality in the other general purpose processors, embedded processors, GPUs and DSPs and so on. Whereas in FPGAs it is completely different. The hardware component itself is programmed. Here programming meaning we choose the interconnects, we choose the LUTs and we choose the multiplexers and then flip flops and so on for the desirable function, digital functions to be implemented on the FPGA. So, this is the physical hardware is programmed instead of writing the code. Here also we write a code, we will come back to that how this writing code helps in this programming. So, here programming meaning we are actually programming the physical hardware of the FPGA. So, the interconnections and processing rules, as I told, these are created after the programming, that is meant selection. By selection only we are establishing the interconnections and the processing rules, whereas in other processes it is a predefined hardware. You write a code and that the functionality is fixed on that to exploit the hardware which is existing in that. So, here it is flexible and reconfigurable the programming. You can choose any logic blocks in that and in interconnects. Of course, it should be optimized. The shorter connections would be better performance. So, for the performance and other things it would be optimized. So, in continuing with the programmability, some of the FPGAs can be programmed, reprogrammed many times. So, there is a facility of this. So, there are some classifications of the FPGAs which have come up over the years. The flash based ones are reprogrammable up to a number of times. Sometimes, like it is a non-volatile in nature, that is the device is once programmed, the functionality is retained. So, once you put it in the flash, it is retained. If the power is off and then still the program is still there, the design which you have and deployed in the FPGA is still there, and if the switch is off, power switch is off, it is still there, and then if you again switch it on, the same design can be taken again back if it is programmed in the flash based FPGAs. That is reprogrammable. Once it is put in the flash and this program is existing, and then you can reprogram it again with another design, so that the latest design is retained in the flash based FPGAs. So, where anti-fuse FPGAs, that is another category in which you can program only once. So, here the hardware is costly, and if you once program it, you cannot do anything else on that. This is one time programmable, the anti-fuse FPGAs. And then the next one comes the SRAM FPGAs, the third category, which is the static random access memory, which is fully reprogrammable. So, it is configured for this functionality, and it can be programmed each time a reset or a power off. So, if it is a volatile in nature, so whereas this if you reset, the power whatever is programmed goes off. So, again you have to program it. So, this is the SRAM, the static random access memory based FPGAs. So, there are three categories of FPGAs. So, when we say the programmability, hardware is programmed here in FPGAs, and there are three types which depends on the FPGAs. This program can be retained, or it is reprogrammed, or one time programmed, and so on. So, if we come to this, how do you program this FPGAs. So, the description, the language used for programming these FPGAs is the hardware description language, that is commonly called as HDL languages. There are two types of HDLs, that is the hardware description language, even then other category could be added. So, we will see them in the subsequent lectures, how this what is the classification of HDL, and then that is Verilog and VHDL, so on, system Verilog and so on. So, here the HDL, it resembles to a software like any other language, but there are key differences with that. So, we do not say that we are using the software we are programming, it is hardware programming. So, HDL describes hardware using software like coding. So, the software like coding, when we write the HDL code and that describes the hardware, actually we are targeting about the LUTs and if we say when we write the software code, we should keep in mind that we are targeting the resources which are shown in the FPGA architecture, that is LUTs and the interconnects and the flip flops and the multiplexers, so on. So, the programming involves the following. So, it is not like just writing the code and in like other languages, it includes the architecture definitions. The programming involves the architecture, what is the architecture we use, and then what is the functionality we expect from this code or the design, digital design. Also, the physical constraints used in the design, like the ones of timing. So, the timing is the biggest constraint in the design. So, the timing should be taken care. So, we have to execute the signal, suppose for a simple AND gate or the multiplexer, the combinational circuits, also the sequential circuits. So, this needs to be, the decision should be taken within one clock cycle. So, timing is another constraint. So, the delays involved in the logic gates used in the design, so is also are accountable. So, the timing is one physical constraint which should be taken care in the design. Also, the routing, which should be identifying the critical paths, that the shortest the routing, the performance would be better, and the input output interfaces, which interfaces we are going to use. This is also a part of programming here. And then the pin outs to the chip. So, the IO blocks which we are using. So, these IO blocks generally used to interface with the external circuitry, or like the analog to digital converters, or the sensor inputs, or the display outputs, digital to analog converters. So, these IO blocks are interconnected or interfaced with the external circuitry mainly. So, this special functions, these are also sometimes this IO blocks directly connected to the pins of the FPGAs. So, those IOs can be directly used in some of the other applications which we want to take out the digital signals. So, or we want to feed the digital signals to the FPGA. So, this is input and output blocks. It can be a pinouts of the chips, and then voltage level configuration of the pins. So, the pins, it is an LVDS or that is low level differential signaling. What is the type of level configurations in the pins should be told in the program. So, we have to define these in the programs as well. So, in the programming, one is the simulation part and another one is the real time implementation of the code. So, when we come to the real time implementation, these are included like timing, routing, pinouts, and then the voltage levels, all physical constraints needs to be included in the real time implementation, whereas in the simulation part you will define what is the functionality of the code, that will be defined. So, as a whole, if you want to target this FPGA with the DSP systems or the digital systems, so this would involve all these functions. Also, FPGA allows are implementing the different functions that can work in parallel. So, the parallelism is a concept, again very important in this FPGAs, like the two different functions can work in parallel, that is also a part of programming. So, reconfigurability and the flexibility of the design, that is what we mean, that the reconfigurability and parallelism are the powerful tools or powerful techniques of this field programmable gate arrays. So, coming to the challenges of the FPGAs, the FPGA architecture, it looks like memory. If you take the LUTs, those are memories. So, but the design and manufacturing of these LUTs were different from the memory. Okay, so this is one challenge, that it looks like a memory, and the design challenges. So, the second one is that the logic blocks are small. Initially it was small, now it is growing in capacity. So, these blocks, it does not guarantee only one logic block can be used for a single function. So, there should be many logic blocks are required to implement a digital function. So, in that case, we have no guarantee that how many blocks will be used in for the design. So, that is the how many logic blocks. It was very difficult to know in ahead of time that how many logic blocks are required for my design. So, when you do the simulation and then the real time implementation, the synthesis process, we will come to know that the number of logic blocks required for your design. So, suppose it does not fit into the FPGA which you are using, then you have to modify your design. So, to fit into the FPGA which you are using, or the targeted FPGA. So, that is another challenge, the number of logic blocks we are using. Also, the performance depends on the logic blocks, where the logic blocks were placed, and in the, so it's a shorter the interconnect, again the delays will be less, and so the performance will be improved. So, the placement of this your design on the FPGA is decide, or which blocks are used is mainly contributing the performance of the FPGA for your design. So, that is another challenge. So, if we come to this, continuing with these challenges, and it requires placement and routing. So, placement and routing is selecting those lines, again that routing lines for your digital design. So, the performance of this complete design or the finished design, it was not easy to predict in advance. So, the performance depends on the which resources are to be chosen for the particular design. So, and placement and routing is the challenge again in the case of FPGAs. So, the complex electronic design automation software, EDAs, these are the tools are required to fit the design into an FPGA. So, this EDAs these days do a fantastic job to place for your design what are the resources needed and how they are going to be placed, how complex the design may be, the EDAs will take care of it and to fit the design. So, these EDAs are required for your design, the FPGA design. So, you need to use the EDA to target these FPGAs. So, that is another challenge. These complex EDAs, initially one has to learn how to use this EDA software for deploying the code in the FPGA. That is also a challenge. And we have this EDAs mainly, as I told, it involves the design, simulation, and the verification and implementation of these digital circuits, maybe the complex digital circuits. The design of digital US circuit is done by this, it is the job of this EDAs. So, once you have your design or the simple one, multiplexer, AND gate, or any of the digital circuits, then you will be writing the HDL using the EDA, and then the rest of the things have been taken care of by the EDA tools. So, the simulation will be done in that, and the verification is done using the EDA, and also the real time implementation of the circuit to the FPGA, also that means targeting or programming the FPGA is also through the EDA tools. So, the technology review, like to give a bit of a technology review. So, the FPGA device attributes are this: the cost, capacity, and speed and power, as I told you. So, if you see the diagram which is shown over here, the graph of 1985 to 2010 and 12, 13, 14, those years, and still it is continuing. The graph is not finished at this point, and it would continue. So, if you see that capacity, it is increasing, it is keep on increasing. The red graph, or the red line, shows that it is keep on increasing the factor. Okay, you can see that here it has reached up to this here around approximately this 10,000. 10,000. So, so we can say, so we will come back to this again. So, the capacity is increasing in a factor, and then the speed also is increasing. You can see that the blue curve, which is increasing over the 100, the factor of 100, the speed. So, it is over the FPGA architecture, the technology which is being improved through the years has shown this type of factors, which are like, one is the capacity, another one is the speed, which is also increasing. Whereas, if you see the green curve, the price cost we are trying to reduce it, okay, and then the power is also reduced, the power consumption should be reduced in the FPGAs. So, the cost and the cost per unit, or the power consumption per unit, is also getting reduced here, and the capacity is increasing in a factor, and the speed of the device is also increasing. The capacity means that we put more and more devices, more and more transistors in that, so the capability of performing the operations of digital operations are more and more improving in this case, and the speed is also increasing, and the price and power gets reduced. So, it was introduced by Xilinx in 1984. The FPGA first, the technology is introduced by this in 1984, and this term is actually popularized by Actel, an American company earlier. It was that 1988, around that 88, this term is popularized by the Actel. Also, over 30, now it is 40 years on FPGA has evolved dramatically. For example, this capacity is increased over a factor of, that is what we said in this graph, that 10,000 times it is increased a factor, and also the performance is improved by a factor of 100, and the cost and energy per operation was also that is decreased by a factor of 1,000. So, you can see the curve, which is good improvement in the technology. Also, the Moore's law and the plays this important role in the FPGA evaluation. This evaluation, the transistor count doubles every 2 years approximately. So, that gives qualitative changes in the FPGA architecture. So, as many transistors can be accommodated by devices, keep increasing the transistor counts. So, in every day, so the FPGA architecture is more and more dramatically increasing, and their applications also. The corresponding tools, EDA tools, and the softwares are also getting involved, and the changes qualitative changes are happening in those lines as well. So, the Moore's law and the evolution of FPGA can be linked in this way. So, there are 3 different ages this technology improvement can be categorized. Those are the 3 distinct epochs. One is that FPGA invention, and the second one is this FPGA expansion, that is the age of expansion and age of invention, we can call them, and another one is this age of accumulation. So, this is listed only the 3 distinct epochs of this 1984, that from the first FPGA to this 8 years of period of 1991, and again another 92 to 1999, there is expansion of this, and then the third one is this age of accumulation, where this 2000 to 2007 is another 8 years of FPGA evolution. So, what happened in these 3 ages? So, we would be discussing that in the coming slides. So, the first commercial FPGA is that Xilinx, and we told that XE2064, this is the picture of it, of the chip, that embedded chip FPGA, and this consists of 85,000 transistors. Very first one, that XE2064, contained this 85,000 transistors, and we see the logic blocks, those are 64 logic blocks. Compare the picture of the generic FPGA logic block, that is 64, the 4x4 which I had shown. The 64 logic blocks, each has 3 input LUTs and a register. Initially, to start with, they had this, each block has this 3 input LUTs and 58 IO blocks in that FPGA, first one. Now, but the advanced, today's most advanced, that is AMD FPGAs, advanced micro devices, contains the premium VP1902. It features this 138 billion transistors. So, you can imagine that 85,000 transistors, and now we are at 138 billion transistors, and then 18.5 million logic cells. So, it is not it is not the logic block, it is having the logic cells, and then 2654, that is 2654 IO blocks, also up to 6864 DSP 58 engines. Now, they are incorporating the more and more blocks in the more and more device blocks, in the sense that we are going to see what are in that DSP is one part of it, that is the engine, DSP engine is also has become part of this FPGAs, and hard IPs for memory, security and interfacing technologies have been included in this current one. So, these are the features which are being evolving over the years, and wherein from starting with 85,000 and now this AMDs have this 138 billion transistors. So, the here the features, when we take the features of the FPGAs and the FPGA family. So, if we take this architecture has a family of FPGAs. So, the family of XC2000. Okay, so the Xilinx, so here it had gates, registers and routing, that is the only thing. When we come to the next advancements, they have added in that XC3000 is that 3-state bus is added as another part. And if you look at the XC4000, it is the dedicated arithmetic options have been added. Also, the 4000 had memory additions. The Flex FPGA family added with RAM blocks for storing, and the CAL and XC6200 had the dynamic reconfigurations, like the reconfiguration can be dynamically changeable. So, that is another advantage of in 6000 series. And next comes the universal IOs, that is Vertex. This input outputs can be used for many things, that is, and the Vertex also had this LVDS IOs, that is this input output pins, that is the low voltage differential signaling is added in the Vertex, and programmable clock is another part of that, is also in Vertex. Microprocessor part is added in Excalibur. The source synchronous transceivers are being part of this FPGAs in the transmitting and receiving options have been added in the Vertex 2. Also, Vertex 2 add the encryption facilities of that bitstream. So, bitstream is the used to download the codes in the FPGAs. So, these bitstream had been encrypted for the security in Vertex 2, and Vertex 2 Pro is also having these transceivers transmitting and receiving modules. The multipliers were Vertex 4. So, the multipliers are very much useful in DSP elements. So, when we try to design the DSPs in the FPGAs, so we need this multipliers. So, for example, the filter designs, you may need the delays and the multipliers. So, the multipliers was the greatest resource in the FPGA. So, the addition of multipliers in the Vertex 4 is a different brought the different changes in the architectures. Also, Ethernet MAC, also the peripheral component interfaces, Express PCIe expresses in Vertex 5. So, the system monitoring was the biggest part also in the Vertex 6. Vertex 7 added analog to digital converters. So, that is that module, I mean interfacing module for ADC to the Vertex 7. So, the analog signal can be captured and converted into digital signal and fed to this FPGAs. So, instead of having this external modules, and it is introduced with this is added in the Vertex 7 one. Also, the floating point arithmetic is added in StatX 10. So, these are the Xilinx family, and the StatX 10 comes into the Altera family, Altera FPGA family. So, Xilinx is a one vendor and the Altera is another vendor. Now, this Altera vendor is moved on to the Intel FPGAs. So, these are the features over the years added into the FPGAs or the FPGA families, different families of Xilinx and the Altera. So, we have seen that to start with, what is the architecture of the FPGA and what are the components in the architecture. For example, this LUTs, interconnects and the switches and IO blocks, these are the 4 main components, and how this can be used in the FPGAs we will see in the next classes. Also, we had taken into the technology review and programmability and how we can use how we can program this, how the hardware is being programmed in the FPGAs, which is very different from the other language programming and other processors, mainly in the general purpose processors and the GPUs and the embedded processors and so on. Also, what are the challenges in the FPGAs? Mainly the LUT, the logic blocks are fixed for the FPGA. So, and we need to use this or customize this during the programming, and in selecting them. So, the design require how many logic blocks is a real challenge. To know that in ahead of time is a challenge. Also, the performance is based on which one will be the placement and routing. Routing is the important step in the programming, and the performance depends on that. So, the challenges and the programmability, this is reconfigurable and it is flexible, this fully programmable, and over the years the many features have been added and still it is being added now. And what are these 3 ages of invention, expansion and accumulation, we will see in the next class. Thank you.